Hello everybody, hope everybody is doing great. Today I have brought a video which will help you understand the basics of Newton's laws of motion. We will be dealing with some very basic understanding of how to draw a free body diagram and thus enabling us to solve some very simple problems to begin with. Of course, the journey is going to get more and more tougher to deal with, but to begin with, let's have something as easy as possible. So here we have the steps that are required to be followed before you get to solving a free body diagram based problem. The first thing that you will have in a system which is a mechanical system is a set of pulleys or a single pulley, a rope, and masses, and quite a lot of things that can move. So when this is the scenario, there are so many things moving, it's not possible to directly look at an object and say how fast is this going to accelerate, how quickly is it going to cover this distance, and things like this. Well, Newton's laws of motion's free body diagram is an excellent tool in order to get to these understanding about what a system would do when it is let go, when it is under the influence of an external force, or what would happen internally within the system. So for beginning this particular exercise, we will have to look at some rules here, and I have listed them down for you. The first thing that you will have to do is isolate the body. You simply draw a box and then look at what are the forces that are acting on the box, which is basically the object in that particular system. What I mean by all of this will be very certainly demonstrated in a while, but I want you to concentrate on the rules right now. So you need to isolate the body. Forget what are the forces that the body is applying on the system. You should only look at what are the forces that are acting on the body. So you shouldn't look at what are the forces that the body is applying on the system. So that is immaterial. So we will jot down all the forces that are acting on the body, right? Well, it simply means that if you have a horizontal table and then you have a mass sitting there, let's say mass is m, then you ask a question, why is this mass there and it's not moving, it's not flying away? It's like a book on the table. Why is it that it's where it is? The reason is that the weight of the object, which is in the downward direction, m into g, is the weight of the object, and that is being completely cancelled by the normal reaction, which is acting in the upward direction. So this is the reason why you would say that the mass is right now at rest. In other words, it's in equilibrium. Going further, now for every single situation like this, it's possible to write an equation. For example, here you would write that the normal reaction in this case is equal to the weight of the body, m into g. But let's say that you had a block of mass m and it is being pulled by a force F1 in that direction and a force F2 in this direction. Then you ask me, CRS sir, how is this going to move? I would say that it would accelerate if F1 and F2 are unequal, because these two are vectors, and if they are in opposite directions, they tend to subtract one another. And if they are equal, they get cancelled. But let's assume that F1 is greater than F2, then the total force acting on the system would be F1 minus F2, because they are in opposite direction. Had they been in the same direction, I would have written them as F1 plus F2. So F1 minus F2 is the net force acting on it, and this net force causes an acceleration in the mass. This is exactly the Newton's second law, F equal to m times a. So this is how you would solve free body diagrams, and isolating a mass and then trying to find the unknowns, right? So let's look at a real numerical now on Newton's laws of motion. So here I have a situation. So there are certain number of things that I want to tell you before I begin with the solution of this problem. Number one, the floor on which these masses sit are very, very smooth. So there is no friction out there, number one. Number two, the string that connects the two masses is absolutely massless and it is inextensible. That means it's not possible for you to stretch the string. So having told you that, I would now draw the free body diagram of mass m1. Now just observe how that is done. Let me now just draw the shape of m1. So that is what I would call m1. So here is m1. There is a force that's acting in the forward direction, which is essentially the tension in the rope. Tension is the pulling force that exists in a string or a rope. So let me draw that force in this direction and I'll call that tension T, right? Of course, there are other forces. There is a normal reaction in the upward direction. In addition to that, there is a weight in the downward direction. But you can see here, it's quite a sturdy floor. So the mass is neither going to go down, nor is it going to go up. That means there is no force acting in the vertical direction, which simply means that all the forces are getting cancelled. So you can just make sense of these two. You can write that the normal reaction in this case is equal to mass into acceleration due to gravity. Because it is m1, you would write m1 everywhere. That's it. So, but then sir, there is definitely going to be movement in the horizontal. So it's going to move in the forward direction. So how would you do that now? Very simple. The total force along the horizontal is simply tension T. So you write T, that's the force in the horizontal. This is the force that's going to accelerate it. So the mass of the body is m1 and acceleration would be a. So this is your equation. That makes up your equation. T equal to m1 into a. That's how you draw the free body diagram of mass m1. Now we would be writing the free body diagram of mass m2. Why would you be doing that, sir? Because the question is, we need to calculate the acceleration of the two masses and we also have to calculate the tension in the string. When you have to do that, you've got two unknowns. When you've got two unknowns, it simply means that you have to have two equations to solve it. Else, it would be impossible to do it. So let's write the second masses free body diagram so that I obtain another equation like this one, so that it enables me to solve both of them and get an answer. Let's do it. So we have the free body diagram of mass m2. You like it? Let me do it a little nicely. So just like I did for m1. So I have m1, m2 here, because that's m2. This is the block that I'm drawing. There is a force that's acting in the forward direction. Somebody is pulling it. In addition to that, there is the same tension force that's acting in the forward direction for mass m1. Newton's third law, every action has the same equal and opposite reaction. So if this rope pulls m1 in the forward direction, then the same tension which exists in the rope pulls mass m2 in the backward direction. So the same tension exists in the backward direction. So we have the tension for mass m1 acting in the forward direction and tension for mass m2 acting in the backward direction. Now when this is the situation, we can now write the total force. Quite simple to understand that if there is a force acting, somebody is pulling it from there, it's obvious that the system would start moving in that direction. If this happens, then the total force acting on it would be F minus T. The reason why I write it this way is because force F is certainly greater than T, otherwise M2 wouldn't be going forward. That is equal to M2 into A. This is the equation that is the Newton's second law for M2, right? That's the Newton's second law for M2. You can ask me, sir, why did you write the normal reaction and the weight in the second case? Ideally, it should be written, but then N would simply be equal to M2 into G once again, and that would not serve any purpose in this particular situation. But then, according to the rules, I would definitely want to write that. Let me pull this a little down and then draw those two. Maybe I'll just call this N dash because I've already called that N. And there is an M2G in the downward direction. There is an M2G in the downward direction. Certainly, if you think about it, then here also you will have N dash becoming equal to m2 into g. Now this is the complete free body diagram. But anyway, going further, we have got two equations, and we have to solve these to find the two unknowns. The two unknowns here are the tension and acceleration. So there is tension and acceleration here, there is tension and acceleration here. You can find both of them. Let's find tension first. You just divide both of these equations. If you divide both of these equations, equation 2 divided by equation 1, then what would happen is that F minus T equal to F minus T divided by T would be equal to M2 multiplied by A divided by M1 multiplied by A. You see, A and A would get cancelled. Let's cross multiply. If you cross multiply, you have M1 into F minus M1 into T equal to M2 into T, and then you will have M1 into F being equal to M1 plus M2 multiplied by T. So T would simply be equal to M1 times F divided by M1 plus M2. So this is the equation for tension. That is the equation for tension. Yeah, of course, I have this particular thing of putting that box. Maybe I'll just rewrite it. We have F equal to M1, or rather T equal to M1 into F divided by M1 plus M2. Now that is your equation for tension. All right, that's it. Going further, maybe we will now write down what is the equation for acceleration now that we have found tension. Now don't go about substituting the tension in here. It could become tedious in some cases. So what I would do is simply take the equation 1, not this one, but this one directly, and substitute that in equation 2. So there is m1 into a in place of t. There is a t here, and I'd like to write that as m1 into a. If I did that, then it would become f. I'm just substituting equation 1 in equation 2. Just doing that. So when I do that, we have f minus, in place of t, you can write m1 into a. In place of this t, I'm writing m1 into a, and then this is equal to m2 into a. So we have f equal to m1 plus m2 multiplied by a. So the acceleration of the masses in the forward direction would be equal to f divided by m1 plus m2. So this would be the acceleration. Well, sir, is it required? So if you ask me, CRS sir, is it really required to do these many things to get to the acceleration? There is a shortcut. So the shortcut is very simple. To get to the acceleration of any system for that matter, you can just write the acceleration A is equal to the net pulling force divided by the total mass. So let's try to do this. Well, if you just look at the system and ask what's that force that's pulling it, then the answer would be very straightforward. F is the force that's acting on it. So the acceleration of the system would simply be equal to, look at this, the acceleration of the system would simply be equal to the net pulling force, which is F, divided by the total mass. The total mass is here m1 plus m2, and just put a box, and before you finish drawing the box, you realize that both of these answers are exactly the same. You didn't have to really draw the free body diagram, write two equations, solve them to get to the answer for acceleration. So that's how simple it gets. Yeah, these tricks will really prove to be very helpful in the competitive exams that you are planning to write. But then for now, let's begin with the next question. In this question, we had to find the tension and acceleration, and we have done that. In the next question as well, the question is the same. You have to find the acceleration and the tension, but this time the masses have been placed a little differently. We have a pulley. Here in this pulley, the pulley is massless. So that's one thing I would like to tell you up front. So the pulley is massless. In addition to that, the string out there also is massless and it is inextensible. It means you can't stretch it. Having told you both of them, let me now draw the free body diagram for mass M1. I would like you to pause the video. I'm sorry. I'd like to pause the video and try to draw this yourself. So I'm drawing the free body diagram for mass M1 here. So this is mass M1. This is mass M1. I'll just assume in this case that M2 is heavier than M1. If M2 is heavier than M1, it's quite easy to guess what happens. M2 comes down and M1 goes up. That's exactly what's going to happen. So let me draw the free body diagram of mass M1. We have the weight acting in the downward direction. So I'd like to call that M1 into G. That's the weight acting in the downward direction. The mass M1 is being held by a rope, and what force exists in a rope? It's called tension. The tension acts in the upward direction, so that's T. Those are the only two forces acting on this particular mass right now. Then I told you that M2 is heavier. That's an assumption. What if it is not so? Very simple. Instead of writing, if M1 is not so heavy, M1 is going to go up. If it's going up, you would write T minus M1 into G. If it's going down, you would write M1G minus T. That's the only difference. So let's come back here and write down what happens to the tension out here. Well, the tension minus M1 into G must give you mass of 1 into acceleration, because the tension pulls it up, the weight pulls it down, but mass M1 is going up, which means T must be greater than M1G. So the net force acting on it is T minus mg, because they are in opposite direction. Same logic as in the previous case. So now we have this particular equation, and that forms our first equation. Let me draw the free body diagram for the second mass as well. So let me draw the free body diagram for the second mass. So we have mass M2 this time. We have mass M2, and M2 experiences the same tension. So what a pulley does really here is that it simply changes the direction of the force. The force that was like this has now over the pulley. Now it's the same tension is acting on that mass as well. So when that is the situation, tension acts in the upward direction, and then the weight acts in the downward direction. Let me call that M2 into G. Now mass M2 being heavier is going to go down. That means M2G is a bigger force and T is a smaller force. The free body diagram's equation in this case would be M2G, which is the bigger, minus the smaller, which is T, equal to M2 into A. You need to understand that both of these masses will accelerate at the same rate. Of course, the direction in which they accelerate would be different. They're actually opposite in direction. That's taken care by writing the order of these forces, T minus M1 into G, because T is greater. That means it's going to go up. And here it's M2G minus T, which means it's going to go down. So that direction part has been taken care. So it's only the magnitude. The magnitude for both the masses is going to be the same, and that's why it's A on both, in both equations. So having told you that, let's continue. And this time also we'll be finding the tension. How do we do that? Very simple. We shall divide the two equations. If you divide the two equations, you will have T minus M1 into G, right, divided by M2 into G minus T equal to M1 divided by M2. So that's the equation you will have. A is got cancelled. You want me to write that? No problems. So there is A and there is A, and then it gets cancelled. Very simple. Now let's cross multiply. If you cross multiply, you have M2 multiplied by T minus M1 M2 G equal to M1 M2 into G minus M1 into T. That is what you're going to have. If you bring this here and send that there, you will have M1 plus M2 multiplied by T becoming equal to 2 times m1 plus m2. Maybe I made a tiny mistake there. So equal to, we have 2 times m1 into m2 multiplied by g. So this is what that equation becomes. Now all that you have to do is find the tension. So tension would simply be equal to T equal to 2 times m1 into m2 g divided by m2 into g divided by m1 plus m2. Now that is your equation for the tension. That's the equation for the tension. Now acceleration, once again, we want to find the acceleration, substitute T here. So what would T be? T would be equal to m1 into A plus m1 into G. Substitute this tension here. What do you get? You get m2 into G minus m1 into A minus m1 into G equal to m2 into A. m2 into A. So let's isolate this A. So we have m2 minus m1 multiplied by G equal to m1 plus m2 multiplied by A. So that's what you have. A, the acceleration would now be equal to m2 minus m1 divided by m2 plus m1, if you like it, whole multiplied by G. So this becomes the acceleration. Sir, does your shortcut like in the previous case work here? Certainly it does. So let's try to find out how. Very simple. Now, if you just look at this, the total pulling force that exists here is m1 into g, and the pulling force that exists here is m2 into g. Because they are acting on two different ends of the rod, two different ends of the thread, they have a cancelling effects on each other. Because they are unequal, they would simply get subtracted. So what's the net pulling force here? The net pulling force, dear friends, would simply be equal to acceleration here, okay, acceleration here, A, equal to net pulling force is m2g minus m1g. Sir, why did you write m2g first? Because it's greater, very simple. Divided by total mass, which is m1 plus m2. You just take this as a common factor. You will have m2 minus m1 divided by m2 plus m1 multiplied by g. Now that becomes your equation for acceleration, and that's exactly what you got in the previous case. So, well, having shared this shortcut with you, of course, you should be by now, if you have practiced and if you paused the video, tried that shortcut out, and if you have got this, then you should be enjoying by now. But anyway, going further, let's look at one last problem for this video, because I'm going to get a lot of numericals like these for you. These numericals are really essential for you to step into the realm of Newton's laws of motion. This gets extended to rotational dynamics, and we are going to solve a lot of problems together. These series of videos that you're going to receive on YouTube and other social media platforms are going to help you by leaps and bounds in order to get to that particular college where you've always dreamt to be. So with that promise, let me start with another block. Here I have a block of mass m1 that's sitting on a wedge, right? So let me draw the whole thing for you. So we have the block, right? So the block mass m1 is what I'm trying to draw. Let me also draw the wedge. So here is the wedge, and the question says that the wedge basically makes an angle alpha out there. So let me draw this angle as alpha. That's alpha, right? The mass of the object there is m1, right? Sir, if you ask me, sir, how do I draw forces now? Very simple. It's the same forces, the force that you will draw. Let me draw the real forces first, right? So the real forces would be these. Look, the weight is going to act in the downward direction. You call that m1 into g. And then there is going to be a normal reaction you can call that N1. There's going to be a normal reaction because there are going to be two normal reactions, one because of this mass, the other because of this second mass, and just writing N1. These are the only two forces. Of course, there is a tension I completely forgot about. There is a tension out here. So here you have a tension acting in this direction. So these are the three forces that are really acting on that mass M1, right? But then you can resolve these forces this way. So let's resolve these forces. I'm just going to resolve the weight because that would be sufficient. Look at this. This M1 into G is going to be broken down into two parts, to this side and to that side. You need to understand, just by very basic understanding of angles, you'll be able to figure out that this angle is also alpha, that angle is also alpha. So this is something that you will have to keep in your head, that every time there is weight vector and the perpendicular to the plane, perpendicular to the inclined plane, perpendicular to the surface, the angle between them is the same angle as that of the angle of inclination, which is alpha in this case. So we can certainly resolve mg. Alpha sticks to this axis, so you can call it m1 into g cos alpha, and okay, cos alpha, and this, the other component would simply be m1 into g sin alpha, m1 into g sin alpha. So that would be the force onto this side. It's quite clear and understood that the N1, the block is not moving perpendicular to the plane. It's only moving parallel to the inclined plane. That means N1 and M1G cos alpha must be getting cancelled. Otherwise, the mass would be accelerating in a direction perpendicular to that of the plane. So you can simply now write that N1 and M1G cos alpha are equal, but that doesn't serve any purpose in this case because we have to be talking about tension and acceleration, and that happens, acceleration is happening along the inclined plane. So I just write this particular equation. I'd want to think that M2 is going down and M1 is going up. If that is the case, M1 is going up would simply tell you that T is greater, tension is greater. T minus M1 into G would be equal to M1 into A. Of course, there is M1 into G sin alpha. That would be equal to M1 into A, right? So this is the net force. That would be the equation. That would be the equation 1 for the first mass. Let me similarly draw the second mass. So here we have the second mass, and let me just tilt this a little, okay, and we have this plane, the inclined plane. Want to just keep this here, want to just keep this particular box on this one, okay, now it's good, right? So in addition to that, there is horizontal, that's the horizontal. Let me mark this angle as beta because that's what the question says, it's beta. Now this mass is M2, the mass M2 is being pulled down with its weight. This time also I'd like to draw all the real forces, right? All the real forces in red color. Let me do that. I have the tension force, the normal reaction force, I'm sorry, I'll call that N2 in a plane perpendicular to that of the incline. And then I have the weight which acts straight down. Let me call it M2 into G. And then there is tension in this direction. So those are the three real forces. Now M2G will have to be broken down in order to analyze this further, because that's not on the coordinate axis. If you think that this is the x-axis and that's the y-axis, this will have to be broken down. Let's break it down. Well, M2G will be resolved in this direction and in this direction. In this direction, I told you that this angle is going to be beta. It's the angle between the weight and the perpendicular to the surface. This is certainly going to be m2 multiplied by g cos beta, and this is going to be m2 multiplied by g sin beta. Now that's what it's going to be. Now, once you figure this out, it's again very easy to write down the equation. I'd like you to pause the video here and write the equation for yourself. But let's do this. Obviously, m2g is now going to go down because this was going up. This is going up. This is going down. So m2g sin beta is greater. You can write m2g sin beta minus t equal to m2 into a. That's your equation. Maybe you can put that also in a box. That's your box. Having written these two equations, you can now solve for tension. The regular way of doing it is simply dividing the two equations. Let's do that. I have m2 multiplied by g sin beta minus t divided by, we have t minus m1 into g sin alpha equal to, we have m2 multiplied by a divided by m1 multiplied by a. So we have a and a getting cancelled. Let's cross multiply. We have m1 multiplied by m2 sin beta minus m1 into t equal to m2 into t minus m1 into m2 into g sin alpha, right? Oh yeah, it's a little smudged there. Maybe I'll just move this a little. Quite difficult. Okay, maybe I'll just erase the whole thing and then write it again. Let me do that. It's an easier job. So we have m1 into m2 g sin beta minus m1 into t equal to m2 into t minus m1 into m2 sin alpha. Okay. Now, if you want to find t, just transfer this here and this here. The tension would simply be equal to 2 times, or rather, it's going to be m1 into m2 multiplied by sin alpha plus sin beta, sin alpha plus sin beta divided by m1 plus m2. Now, that's what your equation becomes. Now, obviously, in the previous case, you look at this. If these angles were 90 degree, here alpha and beta, if they were 90 degree like this, then you would go back to this question. See, because alpha and beta here are 90 degree. When it is 90 degree, sin 90 becomes 1 and sin 90 becomes 1. 1 plus 1 becomes 2. You get 2 times m1 into m2 into g divided by m1 plus m2. Yeah, so that g went missing here. So I want to write that g here. That's the answer you would get. That's the equation for tension. Of course, you can solve for the acceleration. How do you solve for the acceleration? Very simple. Take this equation, substitute in there, and you can get the answer. But then we know the shortcut now. We don't really have to, the first time we wrote it, it became a hypothesis. Second time we used it with another problem. Now it becomes really concrete because it gives you the results all the time. So what's the force that's acting in this direction? Let's try to figure out. The force that's acting in this direction is m2 into g. What is it? Sin beta. Now what's the force that acts in this direction? It's m1 into g sin alpha. So these two are the pulling forces, by the way. And we said that m2 is going to go down and m1 is going to go up. If that is the situation, then obviously m2 into g sin beta must simply be greater than m1 into g sin alpha. That's also a condition to find out whether m2 goes down or it goes up. If m1 into g sine alpha is greater than m2 into sine beta, m2 into g sine beta, m1 is going to go down. Whichever force is greater, that mass is going to go down. It's as simple as that. So having told you that, we have the acceleration A equal to net pulling force. Net pulling force is simply m2 sine beta. I just wrote m2 sine beta. That's one force pulling in that direction. The other force that's pulling in this direction is m1 sine alpha. Sir, you're missing a g. Yeah, I took that out as a common factor, right? So divided by the total mass would be m1 plus m2. Now that becomes your acceleration. That becomes your acceleration. It's as simple as that. So in the next video, let's look at more problems. These are some very basic concepts that everybody needs to know so that you excel in your competitive exams. CRS sir is with you, and let's do it together. Thank you so much. I'll see you in the next video.